This week we're glad to have Yingkun Li from Wisconsin, who will tell us about Motivic action conjecture for Doi-Naganuma lists.
Okay. Thank you very much for the introduction and the invitation to speak here. It's a pleasure to visit. And so today I'll talk about Motivic action conjecture for Doi-Naganuma lists. By the way, is the talk 50 minutes or 1 hour?
1 hour.
Oh, okay. So this is will be about the joint work with Alex Horawa, who is a postdoc at University of Bonn. Okay, so to start, let's start something familiar, I think, to many people. So let x the level and modular curve defined over Q bar. So if you look at the C points of this, then this is just upper half plane for gamma 1n. And maybe you have to compactify by adding some cusps. So small omega will be the Hodge window on X. And for next number, for integer k, we can think about way k modular forms as global sections of omega to the k on this X. Possible. Okay. And because this is X is over Q bar, so you can actually talk about this over Q bar. Here, one has the action of the usual Hecke algebra, which is also you can act on, which is also defined over Q bar. Act on this guy as well. And so somehow besides H0, one could also consider a higher homology. And then this Hecke operator or this Hecke algebra will also act because it's just a correspondence on the underlying X. So maybe let me write I here. And but as we all know, like usually you think about global sections when k is say bigger than or equal to 2, not higher hi, because for high hi this cohomology vanishes. This hi it's trivial. There isn't really much going on here.
Like K, right?
Sorry?
In I? No.
For I bigger than 2. Yeah, thanks. Okay, because you can, I mean, this is one dimension, so essentially just look at H1 and then you can use their duality and then see that that's just H0 x of omega. Okay. So, however, for k equals to 1, this is not trivial. I guess I is also 1. Because by their duality, you just have H0 is same as H1. And you can actually see that using this duality, just over C. And construct a map that looks like this. So you take your F, and then you set to something of taking a suitable coordinate is just to be a weight -1 modular form. So something like this. To apply a suitable power y, so it's holomorphic weight. Maybe also for some differential forms. And you can think of that as an element in H1. And you see that the same set of Hecke eigenvalues appears both H0 and H1. Okay. And now because we know that this H0, H1 is actually can define this over Q bar, it makes sense to try to see if you can normalize this map so that it's actually maybe defined over Q bar. And you can see this sort of this way. So let's suppose F is an eigenform. And if you like, and actually maybe it helps to take maybe a new form for gamma 0n with some Nabin types. Then we know that that by the work of Delay and Sayre, there is an odd, irreducible, and continuous complex representation of the absolute value, absolute Galois group of Q. Odd, irreducible. So odd just means that complex conjugation goes to something with determinant -1. And because this is continuous, the image is finite. And you can look at projective image, which is the finite subgroup of PGL2C, and that's classified by classical work for the Sligo FR. Okay, so now you take this eigenform, and then you can look at just the esotypic part of this cohomology. So and by multiplicity 1, know that this is one-dimensional. And over C is just given by these guys here. So how do you see this guy is rational? Well, for H0, it's not hard. You have the Fourier expansion. Just look at that, and that gives you rationality. For this class in H1, well, you can try to use their duality, which is over Q bar. And so you have to pair this guy with this F. So maybe let me give this guy a name. Call it omega F. So here I don't have to take a pairing of the same eigenspace. I can take some arbitrary guy. And this turns out to be essentially the Peterson inner product between F prime and FC. So FC is it's a countergradient of F. So if F has Fourier expansion, an times q to the n, FC has just a conjugate Fourier coefficients. And if you like, you can take F, take an example where F has real coefficients and FC is the same as F. And in that case, you can also take F prime to be the same as F. And in that case, maybe you want to know what is this Peterson inner product. And it turns out that this is essentially special value of the adjoint function for F at 0, actually. And because F has this associated Galois representation, I can write at 0 as a Galois representation. Okay. Because this rho F, this rho F has finite image, so this I0 rho F also has finite image, and depending on the projective image of rho F bar, you know whether this I0 rho F will have rational character or not. So this is. By Stark's conjecture, this is the logarithm of the F's value of some unit. For UF, in Q bar, that's fixed by the kernel of the Brown representation. In fact, this is null. If the projective image of rho F, if the projective image of rho F, so image of rho F bar is not A5, so in other words, it's solvable. Okay, so if we put this together, then we see that if I somehow define this map so that I mod out by this Peterson norm, which is log of this unit, then this is actually a map that's over Q bar. So this makes sense. Okay. And it turns out that this is a general phenomenon. The fact that the same system of Hecke eigenvalue appears in multiple degrees, in this case in coherent cohomology, and also The cases when you have singular cohomology, it's a general phenomenon. And the philosophy of Venkatesh is this can be described or explained by something so-called a derived Hecke operator. So I put this derived Hecke operator in quotation mark because I think there's a very nice picture, but there's a lot of things that still needs to be proved. So for certain realizations, one can construct this, but I guess not in general. And so today we'll just look at what happens in the coherent cohomology for something a little more complicated modular curve, which is Hilbert modular. Hilbert modular forms, and in particular Hilbert modular surface. Okay, any questions?
Sorry, what specifically can be described this way?
So here you have H0 and H1. A priori there is no, well, in this case there is a Serre duality, but that's really special. So you have only complementary dimensions. I mean, in general, you would have something like HQ plus 1, all the way to HQ plus something. And then the same system appears in all those degrees, and then hopefully you want some operation that goes from 1 degree to the next degree. That's the derived part that increases the index. Yeah, thanks. Any other questions? Okay. So. The conjecture in the case of Hilbert module forms, Hilbert module varieties, this is more or less contained Alex thesis. Yep.
Sorry, I'm just asking silly questions. So I'm
No problem.
slightly confused. H0 x omega and H1 of x omega. Shouldn't Serre duality typically be between like H0 of x? Shouldn't one of those be O, or am I missing something?
It's one dimensional, so you only have 2 degrees,
Right.
top and the bottom.
Yes.
There, the duality is
Right, but should the
you mean there's some conjugation going on?
yeah, there's some there's some well on the coefficients.
Yeah.
The
Yeah, you're right. Thank you for pointing that out. So here you notice that I took this bar,
right.
and then that's the conjugation.
Okay.
Because if you just take F paired with omega F, you get the Peterson interval between F and FC.
Yeah.
And so there's some conjugation going on. Thank you for taking this up. So you can suppose that F is same as FC. Makes life easier.
Maybe another relevant point is the line bundle is the square root of the canonical bundle, so
You have to choose this.
it did so the twist of it happens to be the same as itself.
Okay.
think one always has to be careful taking square root. Okay. So set up some notations. That will be a totally real field. P. Omega is still the same large bundle. So with case parallel with one modular forms. So X will just be some Hilbert modular variety. You say suitably compactified, compactification won't play a role for us. Let's not worry about that today. And then we have the same picture as before. So take an eigenform, maybe new form in some sense. Again, there is Galois representation of rho f. Be a bit careful and then not say it's GL2 of V, where V is some E vector space for some number field. Some number field E, so it's defined over R. So space. And it's two-dimensional, of course.
Excuse me, here, which compactification are you choosing?
You can take a toroidal compactification. It's smooth.
Okay. So,
And then in that case, this omega also extends. The usual omega
would
extends.
you take the subcanonical or the canonical?
You take a subcanonical.
Subcanonical.
So we only care about cusp forms. Okay. Right, then you can look at higher HI. Then you can look at again of isotypic part and the dimension of this. You choose I. So as you would, or as one would expect, in the d equals 1 case, there would be a map from H0 to H1, H1 to H2, and so on. And it's not just any map, it's from this dimension, you can kind of see that this is like a dimension of some wedge product of. And it turns out that there should be some motivic group acting on H0 and then on H1. And so that you can generate all of these HIs from just H0. But this can be described actually quite explicitly without mentioning motives in this case. There's a group called UF. So you can also think of this as a E vector space. Also, it's also dimension D associated again, not to rho f, but to the adjoint of rho f. So here you can think of this. GF goes to the GL of phase zero endomorphisms of V. So this is a three-dimensional. And actions of these HIs. Which let's first describe over C because it's very explicit. So what is this UF? We just some kind of stark unit. For this vector representation. So specifically, I write this as the homomorphisms between S0 rho f, and so maybe I should say that since this is finite, this vector through finite Galois of finite potential f. And we can take. So it doesn't actually matter which L you take, as long as it's a kernel of rho f is fine. So the units here is a finite rank Z module, and then you can tensor with E, think of it as a E vector space. And there's a natural action of your Galois group, so you can think of it as a module over this group ring. And same thing here, and these are the homomorphisms between these modules. Yeah, and actually explicitly, with a bit of work, you can write this out the following way. So zero endomorphisms, and then say you tensor with C, so consider this as a C vector space. And now here, maybe I should, you should always fix an embedding of Q bar to C. And with respect to this fixed embedding, think of L as a subfield of C, and then there's complex conjugation out there. And by the different real embeddings of F, you get actually D complex conjugations. Let's call those CJs. Complex conjugations. And you want to take the part that's fixed by all of this. Right, and as we said that this rho f is an odd representation. So the determinant of the complex conjugation is -1. So how should we see, how could one think of this? Okay, this is a three-dimensional vector space. And then I have my action of S0 rho f. So rho f acts by let's say, choose a basis, so it's my fixed complex conjugation, let's say it's 1 minus 1. And then what about rho f of C1? Well, how does this act? This is just conjugation by this guy. And what am I conjugating? I'm conjugating trace zero matrices. So I can choose a basis so that the diagonal ones actually get fixed, but then the off diagonal ones get -1. So with respect to that basis, you get something like this. And you also take a part that's fixed by complex conjugation, so it's one dimension. Actually, I think it's an E-vector space. Yeah, sorry, maybe I should have said this is an E-vector space. But then, of course, we can't tensor everything. With C, okay, and now we can talk about what is the action on HI.
So is that equality conjectural or?
Sorry?
Is that equality conjectural or?
No, it's just some calculations, the dot.
But this means that at naught of rho f appears in the units of L. In that.
I mean, this is just the definition of the UF. I didn't say what's the action yet. And I didn't tell you how they should be compatible.
But you say that it's d-dimensional.
Which one? This one?
To me, why isn't that UF 0?
Sorry. This UF is d-dimensional.
Yeah.
And?
Isn't that star conjecture?
I think he's just using the structure of units as a Galois module.
There is no Stark conjecture going on here, so I wouldn't use Stark unit group.
Oh, okay.
You're just taking the units, you are tensoring them up with a field. And you
Okay.
cut out a piece of that, okay? It has nothing to do with Stark's conjecture.
So maybe.
No, it's taking the part of this.
It's a unit group.
Yeah.
Okay, so somehow I decompose this d-dimensional E-vector space into really just d one-dimensional E-vector spaces, and then for each one of them, I can tell you an action, and that gives me the action, right? So I can define the action of, so let me call this guy J. It's also tensor C. So let me define this action just by its so-called particle complex conjugation. You can think of this as just sending Cj prime to either itself or so somehow you have to go down to the lower half plane. But if you think of this as an automorphic form, living on L2, then it's okay. And if you say that this UF in other settings, it's replaced by this Motivic. Okay, so now I can say the conjecture. But should be a graded action. Of wedge of this UF. I think one has to take two. On the higher cohomology. Now this is over Q bar, such that it's the same. As the action that's this partial complex conjugation after a tensor with C. It's the same. The action on the left. Any questions? So I first heard about this when Alex gave a talk in a seminar called the International Seminar on the Morphic Forms that we organized. And I was quite intrigued, but also I wasn't really sure what this conjecture entails. But fortunately, he said, you know, what happens in the first non-trivial case when you have a Hilbert modular surface? So that really cleared things up because it's very concrete that I can understand. And work out. Okay, so back here, for a subset of these indices 1 or 2, let me denote omega sub I, which is something in H upper the size of I by the following. So if I is just empty, just say F, I is 1. I should also say that suppose there is this a unit such that is positive, or let me take it's negative, but its target is positive. Okay. Yeah, I always say the upper half plane. Okay. As you can imagine what happens I equals to 2. So something similar happens. It's 1, 2, then you just conjugate. Yeah, so that gives you a basis of this H upper I of C omega. Now, what are the units? In this case, you can write them down. But let me just say, slightly more general, there are 4 units. Uij, which gives you unit regulator matrix. So let me call this action star here. Not star, star. So what is the star here?
What is L?
L is this fixed field of the kernel rho f. So it's just some number field. Okay, so I think before we decompose this d-dimensional guy into, or two-dimensional guy into 2 one-dimensional guys, so let me just say that I can take a generator, which are some explicit basis. UF such that two of them, and the star on Earth, if you flesh out this conjecture, says this basis, you get this 2x2 matrix inverse times omega f1, omega f2. And if you take the wedge, then you just get one of the determinant. And so the conjecture in that case, try this. Okay, erase here. Is that this linear combination of omega f1 and omega f2, this is over QR. And of course, you can say that there's also a H0 and H2 version, but then H0 is just, and check the Fourier expansion, and then H2, you can again use their duality. and then see that it's determinant of this RF. If you can show that that's the adjoint alpha value, then that's the star conjecture. Then,
Yes, let me ask about that a little bit. So
okay,
you have a 2x2 regulator here,
yeah,
yeah? The associated L function has order of vanishing 2 somewhere.
yes, if you take this this example, then this is setting d equals to 2.
The L function has order of vanishing 2.
Yes.
At what point?
Depending on how you normalize.
Well, normalize it for me, any way you want.
Okay,
Give me a point.
Normalize it's
normalize, so it's a red point
at what point?
at 1.
At 1.
Where the functional equation is what?
If you want to get this, you should normalize it so you get it at 0, at s equals 0, order of vanishing 2.
Okay.
Okay, now there is an issue. So this is not a one-dimensional case of Stark's conjecture. Stark doesn't predict, the non-abelian case of Stark doesn't predict the existence of unit of any kind.
Uh-huh.
It's a little bit more delicate than that, so.
Okay.
Yeah. But what you're saying to us is that this regulator that you're obtaining,
Uh-huh.
if you compare it to the second derivative of this L function, which has order of vanishing 2 at some point.
Uh-huh.
So if you divide the 2, you get something algebraic.
Uh-huh.
Is that what you're saying? That would start, would say here.
Yes, I think so.
The units, the 4 units. So in this case, you can get your hands on these units.
Oh, I'll give you an example where we can get our hands on
Okay.
units. The base change case. Oh, sort of like first non-trivial case, right?
So you start with rank 1 and you base change and you get something of rank 2.
Oh, you get rank 1 plus 1.
Okay.
So suppose f is change of
Base change, what you call Doi-Naganuma.
that's right. Yeah. That's the in the title. So base change, you can just think that rho f is the restriction of rho f0 to absolute Galois. Then in this case, I can do a rational change of basis to make this RF diagonal. Where the diagonal entries are logs of units. And here, this UF0 is really the UF that we've seen in the introduction. This UF0, so it's the adjoint value of F0, and this is the adjoint function or the adjoint representation of F0 tensored with chi f, or the character of F over Q. And there you also get units.
So in this case, the L function in question is a product of 2 L functions. Each of them has order of vanishing 1.
Yes, 2 is 1 plus 1. Okay, then this conjecture is equivalent to saying that I take the right linear combination of omega f1 and omega f2, and divide by the log of this unit. This should be over Q bar. Okay. So the conjecture bomb is equivalent to this, and what we showed, put it here, so there's more space. So let's say F0 has level n, and F has ribbon D up to some technical condition. D and N. And the image of the projective representation of F0 is not A5. Then the conjecture is true. And I should say that the condition on D and N, they are just technical conditions that with a bit more work you should be able to remove. And this other assumption that the projective image is not A5, this is, as we have already seen, this is just this I think is Starr's conjecture. Because in the solvable case, you know that at zero of this representation has rational characters, and then Starr proves this conjecture in those cases. Okay, so any questions? Okay. So since it's 1 hour instead of 50 minutes, I guess I still have 9 minutes, and then I can say a bit about the idea of the proof. Okay, so first, one notice that there is this algebraic swap map that stands your coordinates Z1, Z2 to Z2, Z1. Okay. This, in fact, gives you a map or gives you an involution on HI. So you can decompose this H1 into the plus or minus part. And then it's not hard to show that see. Also the F. So I think here one really need to take that F is a base change, because otherwise if you swap, you get some other form. This is conventional, and over C is spanned by eta plus minus. So I just have to determine the scalar. And somehow, with t equals 2, one uses this substitutional isogeny between SL2 over F and for Q. Maybe let me say OV over Q, and this V is like F plus Q squared. This is not the same V as before. And this is just for F is real quadratic, or F is quadratic. Okay. And so now on this orthogonal Hilbert variety, you have special cycles. What you can do is you can pull these classes back to these special cycles, and there, your small omega becomes capital omega, and then you can, it's a top degree form, then you can integrate and then get that scalar. Of course, if you do this, you could very well get 0. And that happens precisely when your F, well, that happens if your F is not a base change form. If it's not a base change form. If it is a base change form, you could still get 0. But the chance of that is actually low. And then we can show that that doesn't happen, and then actually get a scalar. And it turns out that scalar, so I think we did it for this guy here. And this you can also write it as a ratio of the Peterson norms of F at F0. So maybe from here you can kind of see how this goes. Yeah, how do you see this? How this goes? So this is this is the idea, and to execute this idea, you would need to consider so, or to realize this, yeah, let me say realize these theta lift, realize space change. Yeah, so in other words, write your F as a theta integral of F0 against the kernel. And then you write it back, F0 is the integral of F against the same kernel of a conjugated. And then if you just play around with these two equations, you actually see that the C is this ratio. Okay. Yeah, so this is roughly the idea, but to execute it, there's a lot of tricky parts, at least for us. For one thing, the usual theta correspondence is between symplectic group and orthogonal group. So in this case, SL2 and OV but we actually have to work with the theta correspondence for the for GL2 and GO. So it's unavoidable because you have this F and F0, which has Lipid types. That makes things quite tricky. And the cycle that we get, actually, you see that it's some weighted cycle, but there's also the character in there. But in any case, this is a rather valid idea that one can also try to generalize. So some generalizations. Oh, you can relativize the situation. So replace Q by some totally real base field. F0. So degree D0, this is degree 2D0. And these are all totally real. Then you consider base change of something on F0 to F. So let's say this is the base change of F0. And then similarly, you can define these omega i's. So maybe you also see that the places below you have E infinite places and each of it split. Into pairs V1, V1 prime, V2, V2 prime, so on. Now you can suppose there's some rational subspace in this middle dimension. Such that if you tensor it with C, this is a span of those omega of upper i's, where I is subset of this V1 prime and so on, VD prime, and I intersect I prime. This is empty. So by I prime, I just mean that I replace an I just look at its prime guy. So in other words, you shouldn't have, say, Vj prime in this both in I. And of course, size of I is 0. Okay. Yeah, so if there is such a rational guy, then one can hope to show that if you have omega f I plus omega f I prime, and then now here your regulator matrix, I should say, this is log diagonal. There's one for F0, and there's one where you twist by the character F over F0. So one would expect to show that the analog of the case when F0 is Q should also hold in this case. Yeah. Okay. Sorry for the time. I'll stop. Thank you. Yes.
This reference, the oblique reference to motives, you were saying, is this related to the plectic conjecture of Nekovar and Scholl?
I'm not sure, sorry. Not familiar with, I've heard of it, but I don't know the content of that, plectic conjecture.
So you must be using the Wallace inner product formula at some point to make this proof that this counts, right?
Oh, here.
Pin down the C to relate it.
Oh, yeah, sure.
Yeah.
But I don't know, like, you can just directly play around with these two equations and then get C as this ratio. Like, I don't know, like plug this in for F, change the order of integration. Yeah. But I think, yeah, it's essentially Wallace in the product.
To get a relation with the log of the unit, you go via the L function.
Yeah, here you have the adjoint L function, ratio of the adjoint
Oh,
L.
is this because you just know that they're adjoints?
Yeah.
All right, if there are no more questions, let's thank you.